All right, this is our video on the comparative analysis of 3 different implementations for detecting face masks.
Hello, everyone. I'm Archit. I was responsible for implementing the machine learning classifier.
Hi, everyone. I'm Peter. I was responsible for doing the data pipeline and integration for this project.
Hi, everyone. I'm Liam, and I worked on the edge detection implementation.
Hi, everyone. I'm James, and I was responsible for the feature detection implementation.
Cool. So for the project summary and key results, essentially, our project aimed to build on previous work in computer vision to determine a recommendation for a most balanced real-time building admission system. In order to come to our conclusion, we compared 3 mask detection methods: machine learning classification, facial landmark, and edge detection. These methods we compared by scores in 3 key metrics that we looked at. These were overall accuracy, class accuracy, and runtime performance. In order to train our models, we utilized OpenCV, TensorFlow, sklearn, and dlib. And then key results at a high level: machine learning is the most accurate method, but takes the longest. Face recognition takes about as long as machine learning, but it's not as accurate, potentially due to some light sensitivity issues. And then finally, edge detection is fast, but has the worst accuracy.
So looking at some of the background within the space, the computer vision and facial recognition have a long history. But more recently, mask detection has specifically become a focus point. And within that space, convolutional neural networks and deep learning models are pretty much all you see. Good examples and well-referenced pieces, papers on the topics are by Wu and Seth et al. Respectively. The problem is that none of these talk much about the low-cost implementation. So working with hardware that can't handle machine learning algorithms. And that's kind of what we wanted to explore here.
Some insight into our methodology is that for training, all 3 methods used a common data set of 4 data sets that were pulled from online. And the 4th data set was used as a validation data set to produce our test our results at the end. In the machine learning classification, I used TensorFlow to add CNN and max pooling layers alternatively, and then ended with a flattening layer and a dense layer to make the predictions. I used 80% of the data set for training and 20% for testing.
For feature detection, I used a Gaussian blur to smooth out the images and then pass it through an edge filter to highlight the edges and boundaries, and then pass both of those through a constellation feature constellation method within the dlib library. Once the face was identified, then used feature isolation to pick out the specific feature points on the face.
And lastly, for the edge-based implementation, I created a function that would take in an image and return a vector of edges. So this function would find the edges using a canny edge detector with CV2. And then once the edges were found, I flattened that image into a vector that could be used as training data, which we used to train our edge detection model using sklearn. Our initial model struggled with accuracy initially, though, so we decided to refactor using TensorFlow to attempt to improve some of the performance metrics.
So to obtain the results shown in this slide, we ran all the methods against the same data set, which has 1,006 images in total, with a number of images equally distributed across the with mask and the without mask categories. The first obvious observation is that the machine learning classifier has the best overall accuracy of 96%, with an F1 score of 96% also. The facial landmark method takes equal the amount of time to run the detections, but it is 13.5% less accurate than the machine learning classifier. The edge detection method has only 61% overall accuracy, but the without mask accuracy is actually 1% better than the facial landmark method. One possible explanation why edge detection works better for the without mask category is that when a person is not wearing a mask, there are more edges for the model to train on and do the classification. Next slide, please. So here are some recorded demo videos for all the methods without mask on. For all these videos, I was moving forward and backwards and was trying to see if it will affect how the individual methods will behave. For example, one thing we noticed was that for the facial landmark method, if I moved really closely to the camera, it will always say I was wearing a mask, even though I was not. And similar to the last slide, these demos show all the methods, but with a mask on this time. By doing this kind of experiment, we can find the potential weakness of each method, such as light sensitivity and proximity to the camera, which might help us to improve our methods.
So all of these experiments led us to these observations and conclusions. For all three methods, we observed that due to lightings, the classifier would sometimes misclassify the images. And in the end, after verifying everything, we concluded that the ML classification is the best option for controlled admission to a building.
What we found is that by working with the adverse lighting conditions, we can probably improve these substantially. So that would be an obvious next step. In addition, contextualizing the mask types would be another major improvement to the models, as that would allow us to determine whether or not the mask is within the acceptable types for entrance. And thank you, guys.
Thank you.
Thank you.
Thank you.
Have a nice day.